So the last piece, so Dave and I were out on a hike this morning and he was asking me, all right, so what's your goal for this workshop? What's success? And for me, it is always really to see how we can help the community, and we work our tails off. Raise your hand if you are on the ASO team and you worked less than 40 hours during the week during season. Except for Grace. Right. So I love this quote from George Bernard Shaw, and it really sums up the team and what we're about. I am of the opinion that my life belongs to the whole community. And as long as I live, it is my privilege to do for it what I can. I want to be thoroughly used up when I die, for the harder I work, the more I live. I rejoice in life for its own sake. Life is no brief candle to me. It is a sort of splendid torch which I have got hold of for the moment. I want to make it burn as brightly as possible before handing it on to future generations. So that's what we're about, and that's what we want out of this workshop. All right, I'm going to stop there. And we can switch over to Erin's slides. So I'm going to introduce Erin Urquhart. And Erin is the program manager for Earth Action Water Resource Program. And the reason I'm having to slow down for that is that it used to be NASA Applied Sciences Water Resources. But they've got a new trick name and emphasis going forward. So we met last January, I think it was, at the California Irrigation Institute out in Sacramento. Yeah. And we were on a panel together, and Erin, I think, was in her first 2 or 3 weeks of being on the job. And I said to her, oh, wait, you're the new Brad Dorn. Brad Dorn was the program manager for water resources and applied sciences for a long time. And so I sat and listened to her give her talk. She came, sat down. I said, okay, the ASO workshop is in September and you'll be giving a keynote. And so here we are. But Erin's background is really in water quality and working with satellite data, and in particular leading the pre-launch applications program for the PACE mission, which is up now and collecting data. So you're still shepherding that here and there when you get a chance. So, any rate, Erin Urquhart.
Well, good afternoon, everyone. It's funny because when Tom mentioned that, yeah, I was 2 weeks into my new gig, I didn't know anybody from the irrigation community, and so just hearing from someone that I'd never met on the stage or in the keynote talk, completely forgot about that until 6 weeks ago. Like, hey, can you come to Tahoe? Either Monday or Friday of that week. Well, I'm going to be in California anyways, but yeah, let's just tack it on. So I'm really glad to be here, and I will practice this. But yes, I'm a water quality scientist by training, which I know is very different in this community. And this isn't going to be a snow talk. So I hope that, I can kind of follow in on the quote that you provided, give a little bit of kind of holistic, optimistic hope for this week and kind of moving forward. So like Tom said, I just recently started running the NASA Earth Action Water Resource Program at NASA headquarters. That encompasses both our kind of applied science research portfolio at the Roses, interagency partners, international work, as well as our Western Water Application Office, which is about to say that we help a lot of you guys be familiar. So I'd like you to imagine a world where access to equitable water, a world where fair access to water is kind of pressured by drought, flood, and water quality. And so water use has grown at a rate that's more than 2 times the rate of population growth. And this is really due to expansion, urbanization, and westernization. And this growth is really putting significant pressure on global water resources. So by 2025, which is 114 days from today, according to the UN, 1.8 billion people will live in areas plagued by water scarcity. 2/3 of the world's population will be living in water-stressed regions due to abuse, growth, and climate change. So as these water resources become scarcer, information about water resources is becoming more and more critical. And NASA Earth observation satellites, airborne sensors, as well as our ground-based sensors, can provide unprecedented data for accurate and timely representations of water resource quality, supply, and demand, crucial for addressing these future changes. And so the program that I lead at NASA headquarters and throughout all the NASA centers really does connect water cycle information to Earth observation data with stakeholders and end users on the ground to make actionable impact for water resources. So just to kind of set the stage, I wanted to talk a little bit about kind of water resource management decision-making challenges, the way that I kind of see them. And I invite you to kind of yell out the ones I'm missing, because I'm very vulnerable to strategy and changing the way I kind of think about water resource decision-making. So first off, one thing that we really kind of have a challenge with is designing equitable access to water across different regions and communities. The next is really designing irrigation systems that are going to optimize water use while alleviating food scarcity. We need to improve our treatment and management of wastewater and stormwater systems to protect both human health and water quality. And we really need to get better at coordinating and negotiating water agreements for the shared protection and use of transboundary global waters. My favorite topic, as Tom kind of mentioned, ensuring that we have good health of our inland, coastal, surface, and groundwater quality. The next one is really designing and managing hydropower operations and balancing the need of energy use and the impacts for both environmental and societal needs. And then lastly, really preparing for and assessing the impact of extreme events, so flooding and drought and those impacts on our water resources. So if I've missed some, holler out. And you will notice from this list, I'm not listing snow, I'm not listing sleet, I'm not listing kind of the applied science and the fundamental research. I've really tried to reframe these things and the challenges that I'm seeing within our water resource partners at management agencies. A few weeks ago, when I was really digging into kind of different water management resource agencies, I came across a water management agency in Southern Florida, where on their kind of top list of challenges, they actually have a Python advisory board. And so that's something that in addition to this list, we're finding that in Southern Florida, water managers are also being tasked with dealing with Pythons. So the title of this presentation was Unlocking Opportunity. And, so when I talked to Tom and I kind of said, what are you looking for this presentation? He mentioned tell the origin story, paint the picture of NASA Earth Science to Action. And when I talked to my predecessor, Brad Dorn, about this presentation, one thing that he really highlighted was highlighting and finding opportunities in research. And that's what I really think Tom did. And since then, this company has grown to provide innovative solutions for water management. So the key really is to unlocking those opportunities. What I see is kind of 4 required components. So the first one is really leveraging Earth observation data for precise, accurate, and real-time information on water resources. I could argue equally as important to collaborate and partner with our end user agencies and stakeholders, engage them early and often to make sure that we understand their needs and challenges, so that we're developing solutions that are meeting real world needs. Apply cutting edge emerging technology, AI, machine learning, digital twins, advanced forecasting, so that we can improve the accuracy and the timeliness of these Earth observations. And then lastly, combine this complex data of Earth observations, of advanced forecasting, the hydrologic cycle, develop accessible, innovative tools that water managers can use to make change. And so I think that it's really these kind of main components that are the key to turning research into innovation and sustainable solutions. So I'm quickly going to kind of go through those 4 components as I kind of see them, and I'm going to kind of paint a couple pictures that I've seen that have been really successful. So it couldn't be a NASA talk without showing this. So a lot of people outside this room, when they hear NASA, they think farms and A lot of people don't understand that NASA actually has 34 missions in operation and 7 more in formulation coming. I like to tell the joke that I guess I was probably preparing for the California Irrigation Institute presentation. I was working on my slides, down for the last hour, and I sit down and I have all these slides open. And this poor, probably 15-year-old girl looks over at my slides and she said, "I had no clue NASA looked at Earth." Saddle kid, we had like 5 hours on this plane together. I lost her like 5 minutes in, and she like pulled out a handheld. But regardless, what's really exciting about this is that over 70% of these missions look at global water resources and the water cycle. So I may be biased, but that's really good for our community. So just a quick snapshot of the Earth System Observatory and the kind of the associated NASA missions of the 2020s. So we have missions kind of spanning all the way from, these schematic representations. We have NISAR, I believe it's Mass Change, Great Sea, ASO, SPG, Glimmer, and PACE. And really what I'm trying to show you is that NASA satellites really do span the continuum of solid Earth all the way to kind of the open ocean. In this solid Earth space, we have, estimates of surface composition, surface deformation, aerosols, gases. As we move to the water cycle, we have all of our favorites that you guys kind of know in this room: precip, snow, albedo, groundwater, surface water, water quality, surface flow, etc. In the kind of this terrestrial space, we have measurements of ecosystem health, structure, vegetation traits, physiology, phenology, wetland ecosystems, and so on. And then really in this land sea continuum, we're thinking kind of rivers to estuaries to open coast. We have information on algal blooms, phytoplankton functional types, sedimentation, sea level rise, oil spills, and the list kind of goes on. So digging a little bit more into NASA water data, these variables kind of cover the full water cycle. So precipitation, snow cover, groundwater, water quality indicators, evapotranspiration, soil moisture, surface water. And these Earth observations really do provide that unique perspective on kind of what's going on Earth, both with the large swathable area and the time series. These Earth observations can really provide data sets to managers that are not accessible from ground observations alone. So, and this really kind of provides a foundation for what we need for water resource management. So when people ask me, why does NASA have a water resource program? Well, I think we can probably all agree that a level 1 kind of raw RRS file, that doesn't just automatically get to sustained use of an operational tool in a partner's environment. And there's really a lot of information that goes into that arrow. That arrow goes all over the screen, and the time and the trust and the work that's included in that arrow is huge. So at the very, very basic kind of answer, when people ask me why does NASA have this program, it's not a straightforward process. It includes all those components that I talked about to really get a sustained use of NASA Earth observation data in a partner environment. So that kind of leads into that second component that I mentioned, that really is the component that's necessary for unlocking these opportunities. This really goes beyond providing information. Working with partners within their community is really the cornerstone of the NASA Earth Observation Program, as well as the Water Resources Program. At the heart of everything is really a user, customer-focused approach. And really, when I like to think about what is the biggest difference between fundamental science, earth science, and applied science, it's really the who and the why. So NASA has built and established long partnerships, everything from California DWR to AWRA to EPA to kind of all of our federal partners, as well as our local and state partners. We've also expanded to partners internationally. We have new partners in Peru. But regardless, this conversation always starts the same way. So rather than a NASA scientist coming in the room and saying, I'm a scientist, I know exactly what you need, and I have something to solve your problems, we flip the script. Hey, what do you do? What's your job? What kind of decisions are you trying to make? What are the choices? What are the data sets you use? Who's dependent on your data? And so on. And so we really try to kind of build that partnership from the get-go to make sure that all of the solutions that we're supporting and developing are really truly meeting kind of user needs from the get-go. So, and that's kind of the crux of how NASA is changing, where before NASA was really just an earth science agency.
With the Applied Sciences program, which is now the Earth Action program, we're putting a lot of weight both on the projects that we fund as well as our mission concepts, that the user needs, stakeholder challenges are incorporated from the get-go of mission formulation. A lot of different ways of doing this. The Western Water Application Office is a very large component of the Water Resources Program. It's really the Western arm of the program. They're really well known for doing community assessments across all the 17 Western River basins. They do community assessments and they directly fund RFIs based on things that they heard during these assessments. And so what I've put up here is just a lot of different kind of water challenge topics and examples of needs that they've collected throughout all these different assessments. And with that, they make sure that everything that they're funding and all of their activities is in direct response and working in collaboration with the partner that expressed that need. So the next step is really pulling together the user need, the advanced technology, the advanced modeling, and then these Earth observation capabilities that I mentioned, and kind of finishing that blue arrow and really turning this insight and this research and this Earth science into actionable solutions. So as mentioned, recently NASA kind of had a little bit of a rebranding. And so the Earth Science Division is kind of calling their new strategy Earth Science to Action. And the big goals of Earth Action are to build bridges between foundational research, Earth science research, and applied sciences, to make sure that we can scale our models, our missions, and our data across geographies, across missions to different communities. And then lastly, as I kind of keep honing in on, is everything needs to be bottom up, user-centric. And so making sure that the user-centric challenges and needs that we hear early and often are incorporated. So what I'm showing you right now is kind of the Earth Science to Action pyramid or prism, depending on who you ask. At this base level, that's where NASA really lives. It's this foundational knowledge, it's our technology. It's all 37 plus 7 of those missions that I talked about. That's where we're really applying kind of this emerging technology like AI, foundational modeling, digital twins. From there, we move up to Earth science and applied research. Then we go to solutions, applications, societal value. And then at the top, it's really that capacity building. It's sharing this information, so public understanding exchange. Another way that I really like to think about this is at the base level, this is kind of, I don't know what I hit. There we go. The base level, this is really kind of the knowing of science. And then as we move up, we're learning about what we kind of understand from the science. And then we're building application solutions, and then we're teaching. And so for my modelers in the room, which I heard there's a couple new ones, another way that you can think about this is at this base level, we're building the models. At that second level, we're improving the models, then we're using these models, and then we're transitioning sustainability to our partners. And then we get the virtuous cycle. It's important that this is an iterative cycle. We don't want missions and science to just be doing this in a vacuum for no reason or no why. So at every step of this, there's an expectation that this information that you're learning at the top and throughout all these different levels is being circulated back in. And I would argue that this isn't just one virtuous cycle, that there's a ton of little tiny spinning circles that are feeding what we're learning from our communities back into every single step of what NASA is doing in Earth science. So I'd like to walk through a couple of use cases that I've seen really kind of exemplified these 4 components that I'm talking about. And I want to kind of leave the takeaway of how we're transforming these NASA research into unlocking solutions. So the Navajo Nation, which is kind of centered in the southwest corner of the 4 states, always has droughts, variable water, scarcity of water. So in collaboration with the Navajo Nation, Department of Water Resources, the Desert Research Institute, and the Western Water Application Office, NASA has supported the development of something called the Drought Severity Evaluation Tool, Sept. This tool really aims to bring together in situ data and earth science data to enable mapping, time series analysis, to allow managers to kind of get hands-on experience with understanding how to prepare and respond to drought. So from this, it's allowed managers in the Navajo Nation to, like I said, prepare for drought, to do map analysis and time series analysis, It's enabled them to do kind of, meadow restoration and also look at snow assessments. Another really big impact that's come out of this project is that it's now allowing emergency fund mitigation, funds to be kind of allotted to the mitigation, following drought. It's also allowed them to look at drought severity at a local scale, inside their communities, as well as their chapter boundaries. Another example is it has to do with water quality. So access to clean water is vital for communities as well as ecosystems all over. And NASA's technology can be really nicely used for inland, coastal, nearshore environments. And so in the state of Florida, which is why I know way too much about their pipeline management program, but this is Lake Okeechobee. And if you probably heard in the news in 2016, 2018, Lake Okeechobee, which is the largest lake in the state, had atrocious harmful algal. What at the same time happening is their water levels were rising. So I think I recall remembering that average levels of Lake Okeechobee surface height is about 12 to 15 meters. When it gets above 16 meters, they have to drain this, or they have to let go of water. And what that causes is they have to discharge water both to the western coast and the eastern coast of Florida. So all the harmful algal blooms that are in this lake pass through downstream channels to kind of coastal estuaries, impacting everything on its way. I read a study that said that this is feeding, basically the issue of harmful algal blooms being transferred Lake Okeechobee to the coastal estuaries is, it's exacerbating the red tide issues in coastal Florida. And they're saying that if they were to have another issue like they had in 2016, it would be a multi-billion-dollar economic issue for tourism, management, fisheries, real estate market. So with, in collaboration with the University of Southern Florida, the U.S. Army Corps, the Southern Florida Water Management District, NASA has been using Sentinel-3 data from Olchi to be able to look at harmful algal blooms in Lake Okeechobee. And so what this is doing is they're able to track and monitor and map to understand the timing of harmful algal blooms. They're also looking at these associated downstream canals, and it's helping managers in Southern Florida understand timing of discharge for the least impact in both those downstream communities as well as in coastal communities. And then lastly, I want to take you to the other side of the world. So the Congo River Basin has tributaries that come in at various places. It's very disjointed. There are lots of places with different water amounts, and certain parts of the river give different rise and depths and troughs to different water level. And it's causing some pretty big issues in terms of navigation on the Congo River, making it extremely unsafe to access. So in collaboration with the Congo River, the Congo Basin Water Resources Center, USGS, and NASA and the University of Washington, they're applying Sentinel-1 data and SWOT data to start being able to understand different swaths or different portions of the Congo River. This one specifically is by Finda, DRC. And what this is doing is they're being able to look at different river heights, different river widths and surface flow. And so this accurate flow data is allowing kind of managers in that region to understand timing for navigation, and really kind of for the first time using SWOT data, being able to understand water extent, height, and different things. So bringing this back down to those four components, what I've tried to do here is kind of show that, in my opinion, to transfer earth science research into actual innovative water management solutions, you really need these four components. And through those three use cases I just showed you, all these projects are leveraging Earth observations. They are working in collaboration with the stakeholders and the partners on the ground of real world needs. They're all applying emerging technologies, mostly forecasting and modeling, to transform kind of the timeliness and accuracy of the sensing products. And they're turning these into actual decision-making tools that people on the ground use. So moving forward, I know I got excited that 70% of NASA's existing Earth observation fleet can support water, but I wanted to kind of mention the future of Earth science for water, aside from me now being at the helm. In the next decade, NASA is leading the outpouring of information from space. And so I'm just highlighting kind of two of our most recent missions and then two missions that were coming that we're really excited about. So Starting at the top, I'm highlighting the surface water and ocean topography mission that launched in December of 22. So SWAT is going to provide, you can kind of think about it as global surface water topography around the Earth. And this is made up of, I think it's a Ka band radar, and it's providing surface elevation of water at every 6 to 12 days down to, I think it's 20 to 60 meters inland, but 60 to 100 meters for the global oceans. And so this is allowing us to look at surface flow in ways that we've never been able to. Very excited, really excited about pairing kind of this elevation of water data with some of our other hyperspectral missions, like PACE, which Tom mentioned is kind of my NASA mission of choice, just because I've been involved. But PACE is NASA's first global hyperspectral mission. And so PACE is looking at our global oceans, our global atmospheres, and our terrestrial ecosystems. And so instead of providing kind of your multi-spectral channel bands, it's providing continuous spectral coverage from the UV through the near infrared with specific shortwave infrared channels. So it's allowing us to look at water like we've never been able to see it before, globally every 1 to 2 days. We're looking at our terrestrial ecosystems at hyperspectral resolution that we've never been able to look at before. And then similarly for our atmospheres, basically really advancing the way we look at our atmospheres, clouds. For water folks, this is really exciting for atmospheric preparation purposes over water. The next one up is NISAR, which is launching no earlier than January 2025. That's all I can say there. And NISAR is going to provide surface soil moisture every 6 to 12 days at the spatial scale of individual farm fields. So around 12 meters. This is going to feature 2 synthetic aperture radars, an L band and an S band. And the things that we're really excited about in the water community are surface water extent, land disturbance, like I said, soil moisture, and then also its advanced capability to look at oil spills in our coastal regions. So, and then last but not least is SBG, which is launching, I've heard anywhere from 2027 to 2028. This is going to carry another hyperspectral sensor as well as a thermal sensor. And so this is kind of going to be things like the Landsat, the EcoStress, the emit, kind of next generation of that. The difference between this and PACE is providing resolution at about 1 kilometer, which for inland communities isn't great. SBG is going to be providing resolution down to 20 to 60 meters. It's going to have a little bit kind of coarser to temporal resolution, but pairing SBG with PACE and then another mission that I mentioned with Glimmer, we're going to really be able to now observe hyperspectrally inland waters, rivers, estuaries, global ocean. So that's really, really exciting to move forward. So finishing up here, while technology, expertise, Earth observation, machine learning, AI is really essential for innovation, in my opinion, what's kind of the requirement of all those components I mentioned is the people. Is the unwavering commitment to find solutions and to kind of solve challenges. So the breakthroughs in water management come from individuals, from teams and communities that really kind of keep pushing forward to find these research opportunities that lead to innovative solutions to kind of change kind of global water resource management. As I know everybody in this room knows, and the data docs know, ASO has experienced this, innovation does not come easy. And the journey to innovation is very rarely straightforward. You know, that's really fueled, in my opinion, by the passion for change and the perseverance when people say no over and over and over again. And so just as NASA scientists and engineers are tackling these complex science questions, it's our kind of our communal or shared dedication to solving these challenges that, in my opinion, is really kind of changing the way we do water resource science. So I invite you, as you look to the future and through the rest of the week, that remember that kind of every challenge is an opportunity, and that with passion and perseverance, I do kind of believe that we will be able to change the way we manage water resources for sustainability. With that, thank you.
questions? Joe?
Great talk.
Thank you.
Very clear. Like for people, young people out there thinking about, oh, I want to submit a proposal. You mentioned roses, and what other vehicles are there that are the right way to move to
Yeah, absolutely. So yeah, in addition to kind of the roses process that, you know, a lot of you are more familiar with, both for RNA and applied sciences, I can spill that we will have a roses 25, so be on the lookout for water resource, roses solicitation in the fall. But there's a lot of other opportunities at NASA for kind of early career. I think the one that I've seen have the largest impact in terms of solutions is the NASA Develop program. And so this is kind of an internship program where it's both undergrad, masters, and PhD students are invited to NASA for, I believe it's 10 weeks, paid to actually see this earth science to action in motion. And so these projects are developed with communities, develop interns. They work with local managers for specific projects. I've been involved in ones with Austin, Texas, and Lava Blooms. And through those 12 weeks, we pull in, you know, students that have computer science, machine learning, Earth observation, science policy, science communication. And they come together as kind of a cohort team, and they work with managers on the ground to develop solutions. So that's kind of the most exciting way. And something that I found out most recently is that I think it was like 95% of the developed projects over the past 10 years have directly supported water resources in the agriculture program. So whether that's because my predecessor brought it in, or it's because we kind of see the majority of these techniques coming out of the management agencies focused on water and food. But yeah, so that's a really good question. And then there's just the NASA internship program. So I have 2 internships right now looking at kind of project look back, what worked, how does, you know, what are you using your methodology to work with managers, what's kind of the best approach. So there's a lot of different kind of avenues there.
There's one other, but don't tell her I'm bringing you this, but directed funding happens as well. And if you've got a great idea and there's not a roses call for you, sometimes the program managers go for that.
A single S&P single source. At any time, you can reach out to me and say, hey, I have a brilliant idea, and if I like it, I can say, submit a proposal, and I'll review it. Directly to me, not here to you. Yeah, go ahead.
Thanks, Erin. Great stuff. Big shout out to the Develop program. We actually just this past year supported the Develop program effort with ASO data, partnering with Florida State. I'm excited to see where that's going to go. Keep continuing on that. I was encouraged to see your discussion of what you call the virtuous cycle. This, in my words, moving past the concept of research to operations, which has always seemed linear and unidirectional to me. I wonder, it's some great detail you had there on the different levels of engagement there. Are there particular programs that even beyond the Earth Action program, where NASA is trying to really spur this kind of investments, intellectual investments, beyond just encouraging researchers to engage with practitioners?
Yeah, that's going really well. So with this kind of new Earth Science to Action and my 9 months tenure at NASA headquarters, I've seen 3 different program managers or program scientists hired that don't sit in RNA or Action. They're kind of this cross-disciplinary programs that are getting spun up, and these folks are encouraged or they're kind of mandated to work across the aisle. And so I believe, and I've asked them, like, is this a one-off thing, or are we going to continue seeing this kind of moving forward? And it sounds like in the future that line, you know, that gray line in the sand between kind of the research side of the house, including all of our missions, our program scientists, and kind of the science teams, and then what we're seeing in the applied sciences, it's not going to be black and white. So I do also want to mention that the majority of the ESO and the Keynote survey missions do also have applications programs housed within the science teams at project science centers. And so they're basically, you know, causing change within at the mission formulation level. And so yeah, basically at every level of that prism, the teeny little areas are trying to kind of cross cut. Same thing with ESO, so our Earth Science Technology Office and our Earth Science Data Systems, really trying to kind of break down the black and white kind of barriers between that and applied. So the future's hopeful.
Other questions? Or comments? I have a couple. I'm gonna throw in just a little extra history that we haven't talked about.
Right.
The answer I always give to people when they say, I didn't know NASA did Earth science. The first NASA mission that was successful was the Explorer 1, which got off the launch pad, didn't blow up on the launch pad, but it got off, and it orbited, and it discovered the Van Allen belts. So that was an Earth science mission from the very beginning. And then in 1960, the first camera mapping from space was the TIROS 1. The first thing it mapped was snow in North America. So those were those things. And then I just wanted to, I realized in the introduction, your introduction, I didn't mention really a shout out to the terrestrial hydrology program and the applied sciences program, which is now.
Craig,
What's it-
Ferguson, and Jared Hinton.
Yeah, but what's the term?
Earth science to action.
Earth science to action.
Yeah,
It's applied sciences,
Yep.
right?
Yep.
So at any rate, those two programs at NASA headquarters, when our program was at NASA Jet Propulsion Laboratory, those were the big sponsors for us. But about a third of the funding came from the California Department of Water Resources and that investment in the very beginning. And Erin mentioned the Western Water Applications Office, and very early on in that, they were talking with us about, okay, how did you get in with DWR? How did you get this successful adoption? And mainly we said, well, that's luck, but it really was, we were at the right place at the right time doing the snow science. And, I had a good relationship with Frank Durkee, who was the chief of the California Cooperative Snow Survey Program. And many recognized him as the California Snow Groundhog. At any rate, I called him up and just said, hey, NASA's investing in this. I think it would be really beneficial. And he brought the funding along with that. And so just following on what you were saying, that's exactly how it works, is through those relationships underpinned by the science,
Yep.
the solid,
Yep.
The solid science.
yeah, and that's something, you know, I'm glad you're talking about kind of external investments. That's something that I've been really thinking a lot about, because within applied science and Earth action, in the funded by NASA applied science in the past, there's this long-term expectation that NASA supports you until you transition to the partner agency. But what we're finding is that, you know, the one GIS specialist in the South Florida Water Management District, they don't have the resources, the time, or the expertise to support, and, you know, kind of the data volume of evidence coming from support tools. And so we're starting to experiment or think about, do we bring in external funding opportunities, cost sharing, you know, our commercial partners early in the game to get that added buy-in, that ultimately are the types of partners that are going to be assuming these types of tools in their operational environment for decision making. And so that's an interesting space, but I think it's crucial if we are really expecting long-term sustainability of these solutions.
Absolutely. And so for the water managers who are here and out there in the video land, if you can be open to partnering up with NASA scientists or other scientists through the Applied Sciences program, which is Science to Action, or Science to Action.
There's a lot of
Applied Sciences.
Yeah, Applied Sciences.
Thank you.
Thank you.
Then do, because those teams can bring big resources, you know, and be, as the George Bernard Shaw quote, be a resource to the community, and use them up, turn them up, and make use of it.
That's a mine.
And we have a great
I know
program
it's not.
manager now,
Yeah.
who is full of energy and excitement to carry that on. Any other questions, comments? The last thing I'll say is, just going through your list. So the recent and upcoming missions. So we are going to be using SWOT data. We're going to be using that for the antecedent lake levels going into the snow season. So that we're not having to fly snow-free every year to get the lakes. With SWAT, we can know what that lake level is so that then we can get snow depths on those lakes, something we haven't been able to do previously. And then, of course, with NISAR, the radar mission, there's some hint at some places being able to get snow water equivalent, but needing shallower layers and not wet snowpack. But some of the wetting products of snowpack that will be useful to us to understand the energy state of the snowpack. And then finally, SVG. So SVG is, it says surface biology and geology, but it's really snow biology and geology. And there are three main components to it. And the hydrology component is primarily focused on albedo and snow. And the decadal survey, which ultimately led to SVG being selected as a deliverable.
Yeah.
Designated observation, I think that's what it's called. So the materials for snowpack came primarily out of our mission proposal, which was to do a spaceborne spectrometer. And before that, all of that was built on ASO. So ASO has its core in SVG. So,
Well, fantastic. Thank you for having me.
Wes.
Dr. Mayor, real quick. I'm trying to find a way to dovetail in here. I want to commend you and NASA. But in the way that you're reaching out to the end user. And so I'm doing this on the fly. But help me out here, Dr. Mayor. The ASO program was originally a NASA program. Okay, because NASA was willing to, here's the information, this is the way things work. It has had a very quick, direct, and immediate impact. That is probably like very few other programs.
Yeah.
So I would commend you on that thought process there. That is a success story.
Thank you. All right, with that, thank you all. Thank you for the invite,
Thank you.
and Molly, thank you for all the help. This has been great.
Yeah, thank you, Erin. We're the first stop on the cross-country tour of conferences
If
and
they want to go to
speeches.
JPL and then Boston, that's worth it.
All right, we'll have to send a lot of guys. Thank you. All right, so we will have a quick break here.
All right. So we'll be moving here into the afternoon portion. I guess this whole time is the afternoon, but alas. We'll be going to the ASO updates, so you'll be hearing from all of our lovely team leads about where ASO is at and the past season, the upcoming season, and any other relevant things. So yeah, I'm going to hand it off to Liz Carey, who is our flight team lead. And without further ado, Liz.
All right, so we decided to do this kind of in what we think is the right order, which starts from flight, runs all the way through the processing stuff to the end products and then to the modeling stuff. So it's kind of where we're going with this. So I'll be passing on to our hardware team next. But I just want to talk about the flight operations from this last year. So we flew 3 aircraft this past year, 2024, just like we did in 2023. You can see in the picture there, we've got 95 Sierra, which is our little King Air 90, which is way down at the end. I made a bigger picture of it in there just so you could see what it actually looked like. And then our 2 B200s. We lease these aircraft from Dynamic Aviation, and they support us with pilots and mechanics to keep those aircraft in the air and running. We also work with them to install all of our equipment into the aircraft, which you can see in this picture. Got the Regal scanning LiDAR system, as well as the high-spec spectrometers and a rack full of computer and data recording devices. So we have 11 flight team members. Most of them are sitting out there in the back. Flight team, raise your hands. There they are. Go ask them if you can look at their camera rolls because they're filled with snowy pictures. So they are the ones that fly in the aircraft. They survey and collect the data. But they're also a really awesome, talented group of people that do a whole bunch of other things for ASO. Everything from installing hardware, data processing, delivering products, all of those things. So they're really cool. Go ask them about what they do. And we all fly around and we have lots of pretty pictures, just like this one that shows Yosemite Valley. You can see Half Dome with a little snow cap on top up there. And so this is really how we install the aircraft. We installed 2 in January, 1 in February. After the installation, we fly our calibration flights. We get all of that into this is really weird. Hi. We get all of that into the system, and then we're ready to go collect snow survey data. Yay. All right. This is an example of what we fly. This is actually what the flight operator sees on the plane. This is the Kauai River Basin. We come in and we fly a bunch of pre-planned lines across the basin. I mean, we call it mowing the lawn. We're just going back and forth. And we come up with this, what you see on there, this kind of topographic looking map. Our flights are on average 5 to 6 hours. And then we'll land sometimes and go back up in the air for another 3 or 4 hours. So this past spring, we flew 48 surveys in what we call our California region. We have 3 main bases in California. We have our Mammoth headquarters base, Reno base, and Redding base. Those are specific because they are close to basins and they also have high-speed uploads. We take on the order of about 1 terabyte of data per flight, and so it's really important that we have the fastest speed to get that data up into our system so we can start processing it right away. We also added the Trinity this year. You can see that guy up on the end. And the yellow is the Pitt River and Sacramento McCloud, which we flew last year. We didn't fly it last year, being 2023. We didn't fly it this year in 2024, but hopefully we will be back at it next year. And then here we are with our Colorado operations. We pretty much fly from the north to the south end of the state. We've got 2 primary bases there, Eagle and Gunnison, and we did a total of 26 surveys in April and May. And then we also did a couple of surveys in Wyoming and Utah. We surveyed the northern winds, as well as the Uinta Mountains in Utah. And so we did in Utah. So we did a total of 78 full basin surveys, 550 total flight hours, and we surveyed 64,000 square kilometers of terrain. And so this is looking back at surveys flown for the last 11 years. From 2013 to 2019, of course, we were part of JPL. We had a single aircraft for those surveys. And then we started between 2019 and 2020 as ASO Inc. We actually had a contractor who was flying for us in 2020. They did those 11 surveys. And then we've grown 1, 2, 3 planes as we've moved forward from there. And next year, I think we will probably be doing a little bit, maybe 20% more of what we did this year. So pushing up close to triple digits on our surveys flown per year. Kat always has that reaction whenever I say that. So in preparation for next season, we're doing a bunch of snow-free survey flying right now. We've already collected some, gotten the Trinity, the San Joaquin, and the Pine Nut Ridge done. I was very grateful to see that that was not what was on fire because we just flew it like a week ago. As much as the fire is terrible, I was just glad to see it wasn't that one. We're going to hire at least 1, maybe 2 additional flight operators to beef up our team, look at ways to become more efficient with our flying. And Tom touched on the sustainability aspect of things, so we're looking in ways that we can become more sustainable. Dan's going to talk about some of the improvements to hardware here momentarily, and then improvements to other aspects of what we do. So communicating issues on the plane, data quirks, things like that, that happen, of course, during the season. So we'll be next year, I think, going with the same 3 aircraft, not 4, just 3. We're going to be increasing our flight team and then making improvements. So, and if you're interested in seeing the work that we do in the plane, we're going to be having 95 Sierra at the Truckee Airport on Friday from 10 to noon. So you're welcome to come out there, and we'll be showing off the plane and the equipment and talking about what we do. And I think with that, I'll take questions and then hand off to Dan.
Any questions? No questions.
You can wait
Perfect.
till
No
Friday if you
notes.
want.
All right.
Yeah.
Hi there. Sorry for my naivety. My question here to you is, how do you guys handle jet lag, knowing that you really have to be able to get repeatable information all the time?
Yeah, so fortunately, we tend to land in the same place that we took off. So we don't have to deal with jet lag too much, but it is really exhausting being on the planes, which is why we've got a whole team of flight operators. So we're able to rotate through and support each other when we're out in the field. But yeah, exhaustion is definitely important to us, and we make sure to try to keep our team fresh as much as possible. Oh, yes. So we've moved into 2 pressurized planes now. The 200s both have pressure systems that Dan devised and designed and built. And so that helps a lot. When you don't have to be on oxygen for 6 hours or 10 hours a day, you feel a lot better.
All right, that's a good transition to our next presentation from ASO, Dan Beresford, who is the hardware lead.
Okay, thanks. Yeah, as Molly mentioned, so I'm the hardware research lead for the team. I think that's my title. I'm the token engineer on the team, and so I'm responsible for all the structural and electrical integration of the instruments on the aircraft. So I'm just gonna give a quick overview of the hardware that we have. I think Liz may have actually shown this same photograph. Turns out it's actually really difficult to photograph everything in the aircraft without a fisheye lens. So this is the view as if you were looking in from the aft cabin door. We've got the Regal LiDAR, which is of course, the instrument that gives us our topography data. We've got the 2 high specs, the SWIR and the VNIR spectrometers, and then the electronics rack that has all the brains that runs all of those. Not shown on this, up forward in the cockpit, there's the operator interface where the flight operator sits and takes all the data and drives all those instruments. And then another key component that we never talk about is the pilot display. So up front in the cockpit, there's a little sort of a gaming console type screen, and the operator from the back will feed the pilot's lines, and they can fly them sort of as a video game style, flight line by flight line. So it's very precise. So some of the upgrades that we've made, this was actually started last year, but we added a second one this year. And so this is the pressure dome that Liz mentioned. So instruments that I just showed in the last picture are now contained inside this dome. It's not really a dome, it's a box. We call it a dome. So this allows us to fly above 25,000 feet. And 25,000 feet is because we have a hard upper limit to how high you're allowed to fly without pressurization. A softer limit is more like 24,000 feet. And above that, you have to have a pressurized face mask. Otherwise, you get hemorrhaging in your eyes and such. And so it's even below those altitudes, as Liz mentioned, it's not just a matter of operator comfort. It's really hard on your body to have those kind of pressure changes, and the vibrations and the cold temperatures that you get with an unpressurized cabin lead to mistakes being made in the data acquisition and the quality control. And just from a purely numbers perspective, allowing us to go above 25,000 feet has made the difference in being able to do some of the Colorado surveys in a single flight versus splitting them into multiple flights, which has a lot of advantages. So this keeps the instruments at atmospheric pressure while allowing us to pressurize cabin. So this was an in-house design. So all the way from the CAD to the analysis, FAA approval, and installation, and figuring out the electrical feed-throughs with quite a bit of help from Dynamic Aviation folks. And there is, Kelly, do you know about this? There's interest from Dynamic to license this or possibly buy one. So we should talk about that offline. So some of the other new bits of hardware that we had this season. So we have a new, PIM stands for Payload Interface Mount. It's just the structure that mounts everything to the aircraft. So we have a new version of this for the unpressurized King Air A90. This is in response to some fuel spill issues that we had. No fault of the Dynamic planes. This is the fault of people at various airports fueling the plane incorrectly, spilling fuel, and then it goes into the port, and then it goes into the cabin, and it makes Liz sick, and and causes some issues with some of the optics. And so this was a new design to sort of quasi seal all of that up, at least a liquid seal, if not airtight. So this was another in-house design. We've got some more mundane stuff. We've got a new electrical power distribution system that just allows us to be a little more, we have a lot more room for expansion for new instruments and stuff. We can also do a little bit of power conditioning with this. And then a bunch of miscellaneous small hardware upgrades for this season. We're going away from using our custom data upload machines, our mini servers, to doing more of a laptop modular-based system that the team can just take in a small briefcase. We've got some 3D printed pilot display mounts that are a little bit more modular and easily replaceable, a little bit more robust. And then the operator interface that I mentioned earlier is a much cleaner interface now. And then ongoing work that we're doing for this upcoming season. So I'm working on an additional data acquisition system that'll let us take environmental data, so temperature, pressure, humidity for now, and then hopefully expanding that to maybe an upward-looking instrument to try to correct for sky conditions, and then it'll just be kind of a general data acquisition system for whatever we want to add in the future. So if we come up with some crazy ideas, we can quickly throw extra sensors on the airplane as long as they're small. And then Christina might talk about this later, but we're trying to get some inventory management software so we can be a bit more organized with our hardware. So that's it, pretty much it. That's what's new in the hardware world with ASO. And any questions?
All right. Any questions for Dan? He won't tell you this, but he did build the pressure dome in his garage. So. Right.
I didn't do the machine.
But some.
Just the assembly. Well, a little bit of machine.
Next, we'll have Kat Borman, who's our lead scientist and head of the super team, which she will explain what that's about.
Thank you. We're fastidious. I learned that today. I call it being a pain in the butt. But anyway, it gets our products out, super high quality. So the team is over here. We've got our little Slack icons over there because we're all shy. So we want to be this big on the thing here. But we also have Tom and Jeff. They're both in our super team because They're in there, you know, helping us make sure we get everything right. There's a lot of us because we have a ton of work. We are the ones that turn the information into the snow depth retrievals. We're the ones that do the specialized retrieval of the snow metrics. So you've seen a lot of these kinds of plots, but I just wanted to point out in the JPL era, it was just me and Tom for a really long time. And then we started to get resources. So for me, you know, adding more icons to my little Slack channel is fantastic, and I fully welcome it. What do we even do? Why are we called the super team? I'll only answer one of those questions. So we get about 24 to 36 hours of the 72-hour turnaround time. So that's 72 hours when the wheels hit the ground to when we try and deliver the products. And so we get half, maybe a third of that time. Now I've kind of magnified what super does in the blue here. You know, I've kind of really fleshed it out to make it look really like we do heaps of work. And so flights, you know, they're just one little box over here, and same as Evan's whole and Christina's whole team in the green. But but what I'm saying is, you know, we can see how it all comes together, and we're the ones that make all of these retrievals based on the hard work that those folks do. So they set us up for success, and we try and bring it home. And so this is how all the pieces fit together from my perspective. So last year we did 78 snow products, so 78 of those reports. They're mostly automated, but you'll notice that we can't automate everything. There's certain things that we want to communicate to everybody about the density choices and maybe some of the other things. So it's not really appropriate to automate these reports and get the same information over to everybody. So we hand make these. There's not a lot of hands in there, but there's a lot of reviewing and there's a lot of making sure we say the right things and communicate what we need to, and perhaps not things that are too in the weeds. We don't want to confuse people. So if you have any suggestions, hit me up. Our workload is like everybody, but our workload is not constant throughout the season. And so you can see the two big peaks. What are those two big peaks? We've got time. Yes, thank you. April 1st and May 1st is when we are cranking on about 8 or 9 surveys ready. They're through Evan, flight's done their stuff, they're through Christina, they're sitting on our desk waiting for us to do them. And so that's why we have a lot of people on our team, but also you can see the build up here. And so we are really working on trying to make our stuff faster, because right now we take a bit longer. And then I'm just going to take a little breath because that was a bit stressful. Okay, so planned improvements. Yeah, I'd love to go back. You are looking, it's pretty friggin' cool. Okay, so we're in the Feather Basin. I don't know which survey, I think it's April. And we are just kind of looking obliquely through. The snow is in the blue shades, and the brown is, you know, just not snow. And it's just really pretty to see how it all falls and doesn't stay and sits over there and doesn't go over there. I stare at this all day and I still could sit here and look at this for a really long time. You're welcome. Here's how I think about what we're doing with improvements. If you just want to look at pictures, you could do that. If you want to read bold writing, you could do that. Or if you just want to listen to me rattle it off real quick, I'll do that. So you've heard a lot about this, but things like trying to deal with clouds under the plane and make that a non-issue. Looking at improving our algorithms so we can get the canopy height better and get the DTMs better. And once we get those better coming in, our algorithms will work better. We're revamping the snow density workflow. We did a bit of that last year, but now we're really trying to automate that. There's a lot of flux in that sector because the information coming in is always different. So whether you've got snow courses from 10 days ago, or it just snowed, or you've got this guy went out in the field and took a bunch of measurements, and you know, Alex dug a pit. And so you've got to bring it all in different ways each time. So you can't automate that. We're looking to expand the field program. We had a really successful pilot program last year where we had a few folks that we sent out to get more density measurements to make that snow density workflow more, well, digestible. Let's see, what else are we doing? We're updating our code. Of course we are. We're trying to look at the albedo retrievals and really look at the spectra and try and understand where they're good and where they're less certain, so we can start to filter them out better and get better estimates of the snow albedo. So when we're pushing that into the models, Dave's model or Mark's model, we're getting the right snow melt rates. Again, we're looking to speed everything up. Like I said, we are the bottleneck, which isn't as fun as it sounds. We've been doing a bunch of data management, archiving, all that mature stuff, but stuff that you don't think about until you start having disks fail because you've got too much stuff on them. We're looking at interacting with compute a little more with the way that we hand off data. Evan spoke a bit about that. We're looking to improve some of our science, like core science, relative registration, all those kinds of really nerdy things, but not to say there's anything wrong now, but we're always improving. And I think Joe was saying that we are always improving. So this is the stuff we're working on. We don't need to work on this, but we want to because we want to make it the best. And the last thing is just really formalizing team. I think you'll notice I have the biggest team, and that's just because I'm greedy. And I'm the bottleneck. So there's another pretty picture just of another scene of the same basin. Thank you.
Is Dave up next?
Yeah, you're taking my job.
Okay, I'm just stealing it just to follow up on all those. So, so you're kind of seeing in under the hood with a lot of this, and that goes back to my slide from George Bernard Shaw as us being a service to the community. And what you're seeing here is really the continued innovation and push to scalability. And then you also saw work-life balance in there quite a bit while maintaining the accuracy of products. And very early on, I mentioned how hard this team works, how many hours they work, and the way in which they were going, it was not sustainable. That's why we hired up, which was good. And then likewise, the innovation on the software to take care of those issues that can chew up time is terribly important to really streamline. So, any rate, that's the feed to Dave Gotchis. Did you guys have any questions for Kat? Matt Meadows, come on, I know you have a question.
So while she's loading that, and we're all kind of in the tech business, does anybody know what today was in the tech world? What's that? Everyone's giving it up. No, it wasn't Tech Free Day. That would be nice. Apple Day, right? It was Apple Day. They rolled out all their big products. And so I guess this was our kind of Apple Day. So I leaned over to Logan and said, God, is this our Apple Day? He's like, well, you need to wear a black turtleneck. And I looked down and it's just not going to happen. The plaid snap shirt is as good as it gets for us right now, but we'll work on that. That'll go on our list of development for next year. Who is interested in the forecasts? Anybody? Like how much water comes out of them? Okay, a few. Yeah, all right. So Logan and I got brought in this year to spin up the operational predictions in-house. And I'm not going to belabor this because Tom already showed it. And jump right to this, which is what's been going on for the last 10 months. It's been quite a bit. I would say we're the tail of the dog, and we haven't wagged the dog yet. And so we're going to try hard not to wag the dog because as everybody can see, they have a lot. But we've been getting wagged quite a bit, getting all this stood up. So we both started in November of 2023. Now, some of you know that we were doing some more hydro modeling before we came into ASO, but that was at NCAR, which is a research organization. And for some reason, the National Science Foundation doesn't like companies doing operational prediction on their big publicly funded supercomputers and stuff like that. So it was time to move out, much in the same way that ASO found it's time to move out of NASA. And really, that aside, what it really allows us to do is focus a lot more on building out the capability within ASO. And so coming in, Logan, raise your hand again, Logan, is the primary architect who is able to take all of our existing workflows, data sets, and everything like that, and build it all and install it and get it to run highly efficiently on Amazon's web services, contributing to the 3 petabytes of data that we are amassing on the cloud there. This included the snowpack data assimilation, which for this past year was still direct insertion, although changes are coming. We're going to talk about that. Ensemble predictions of water supply was the flagship product, but this year we rolled out several other products, hydrologic monitoring and forecast products, things like soil moisture and ET. I will not talk a lot more about those, but keep them in your mind. We reduced our production times from somewhere between about 48 to 72 hours to almost all less than 24 hours after we received the survey from Pat in the super team. And so that was a big uptick in our performance there. And then for several of you, we were able to set up some automated special data feeds so that you could pull the data automatically, either through an API service that was hosted at NCAR still, or an Amazon S3 bucket. And so really trying to push things out, the data, as opposed to just reported values, out to folks. We did flow forecasts at 320 locations across 3 states, Colorado, Utah, and California, of course. And we are expanding that further, potentially significantly for 2025. We created over 300 forecast reports, roughly every 2 weeks, give or take, depending on the domain, and after flight. And some of those forecasts are still going on. So if folks have a particular interest in some of the late season flows and things like that, we've continued to run things mostly for just internal examination and usage, although we do have a few stakeholders who are actively looking at some of those flow forecasts. We just had a call with the Upper Gunnison River District this morning, who uses our late season forecast along with the River Forecast Center to help manage some of those reservoirs. So it's been a bit of a haul. I've showed this timeline before. I just want to highlight there's a growing section here of everything that came before the dotted red line and everything that's coming after. And that's really when ASO started contracting work more directly to fund the operational prediction. And then, of course, 2024 marks the year where things really took off in a big way by bringing things in-house. And so you'll see our major expansion here. We had 5 basins in California, 14 in Colorado, and it's essentially 2 in Utah because we straddle a divide for the Deschênes and the Provo rivers there. And so here's our goal for operational prediction. It's good to have a goal in mind when we set out to do this, and this will evolve over time, but this is really what we've been aiming towards. We want to build a leading snowpack analysis and forecasting system that has engineering accuracy, and that's a really tough thing to do when you talk about doing it at scale, not just focusing on one basin at a time, but trying to do it everywhere all the time and across spatial and temporal scales. And we also want to be a clear leader in reduced forecast uncertainty. And everybody, I think, can appreciate the value in that. It's great if you can have a mean bias of 0 over 30 years. But if your error each year is plus or minus 30%, you're not really helping folks that much. And so that's an extreme example. I would not say anybody's doing that right now, but you can understand that we want to be the clear leader in reducing that forecast uncertainty, really through minimizing the sources of uncertainty through the novel data that ASO provides, as well as the physics constraint that the modeling system provides. And so that's what a number of these other bullets are summarizing here. Utilize ASO's unique data in snowpack and landscape to optimize physical constraint on the model, make advances to the model physics, data assimilation, and computational methods, as well as data science to achieve optimal skill, capitalize on our advanced use of that data and HPC-enabled models, cloud computing resources, which we have a theoretical infinite scalability across. And then the last one is really to foster a deep co-development relationship with stakeholders in order to provide both an education and delivery of sort of the best-in-class products. And that's really what I think I've been most surprised at and most glad to see over the last 2 years that we've been doing this. And this year's been a really good example. We've probably done, I don't know, Jeff, 8 already, post-season recaps with people in various basins and things like that. And the back and the forth and the dialogue, God bless Kate, she's not here. She schedules a 45-minute or an hour-long meeting, and we take like 2.5 hours. And it's great. And everybody's like, God, we should wrap this up sometime. But it's just because the discussion gets going and everybody's kind of just getting into it. So this is our operational prediction system. The main thing to take out of this, there's 2 pathways here. The top pathway is our daily updated cycling system. It's running on observed weather and, quote, just the model, and it's keeping us up to date. We will occasionally launch forecasts out of that. And then a flight happens. Super team drops, and M3 works. They drop the 50-meter snow product on us, and now we're like, okay, now we got to get this into the model. So we'll go through our data assimilation process. We'll spin things back up to get a good thermal state of the snowpack, and then we slap it into the big domain and run it, and then generate forecasts from that. As I said, we'll revisit some comments on that data assimilation methodology. These are a lot of the products that folks got to see during either web presentations, meetings, or the forecast reports from the past year. You've got snow water equivalent in the upper left-hand corner, and that's an animating map. And when you see like a big jump in the snow data there, that's when a new flight got assimilated. There's analyses and forecasts of basin integrated suite, kind of the flagship. Everybody likes to see that product in terms of comparing maybe years or different products there. We've got snow melt analyses and forecasts, elevational breakouts of the snowpack from different products. This was one we added this year. Stephen Hove loves this. He's not here right now. Maybe he's online. It's the soil moisture aggregated across elevation bands, and you can kind of see the wave of snow melt happening and soil saturating at low elevations, and then it dries out at low elevations, and the upper elevations get wet. This is a spatial map of soil moisture. So trying to provide a lot more hydrologic context for what's going on in the hydrologic system, in addition to just the snowpack there. And then, of course, the main product is the runoff forecast. This was my attempt to recreate the beauty of what DWR's done in their multi-forecast product there, just to see that I was copying over the data faithfully and calculating the statistics, because now we're in a big statistical evaluation phase. But you would see in a simpler product like that, as well as these tables in the reports. This is all generated through a now in-house visualization and analysis tool we've ported over from NCAR. We're going to continue to use that in the short term, although we are exploring some alternatives for those data services. And of course, the reports themselves. Unlike what Kat just said, where they painstakingly provided a good narrative on what was going on, you found very little narrative in these reports, and we recognize that. And it became a balancing act between cranking out data and getting numbers and some of these products out to people as quickly as possible over all of the basins as we regularly updated that versus providing a lot of detailed narrative. So one thing to keep in mind for next year that's changing, we're going to reduce the frequency of the reports to only come out when there's an ASO flight that gets assimilated into a particular basin. So it'll match a little more what the super team was producing, and as well as what M3 Works is kind of producing. But we're going to increase the cadence of the forecasting and increase the digital service of those forecast numbers to people. So you'll get more and less at the same time. Think about that. Maybe. Okay. Results. It was, I think by all accounts, it was a good year. There was many basins we learned a lot in. There was some basins I think that things happened really well in, and there's basins that certainly need some new work, particularly those that were brand new to us coming in through several of the new projects that spun up, like the Bureau of Reclamation SNOFO products that got funded over the last year. This is a summary of the ASO assimilated wharf hydro forecast for the California B120 sites. So it's not every California site. There's a lot of headwater sites that are in here. These are the main B120 sites. And so you can see, and essentially the dots are a nominal forecast date of the first of the month. All right. And sometimes the forecast didn't fall exactly on the first. That's why I call it nominal. And the trend that we see overall here was that the forecast did start low compared to what ended up happening by the end of the season at that 1st of March forecast. And I think the weather that we saw in the area bore some of that out. So they started low, things bumped up, and then really by the April 1st forecast, things remained within that plus or minus 10% level. And then at times they even squeezed into within the plus or minus 5% level for all of the major basins here. The one that you don't see a forecast for is the San Joaquin. We did generate forecasts for that. They were tracked during the season, but we figured out that there's some natural flow data issues that we're going to go back and revisit. And so before we start calculating statistics on that, we're going to go back and do that verification. So this was sort of a summary, and this is something that you'd expect to see, which is things sort of converging within a narrow band as the season goes on. But I think the thing that we are happy to see here is by April 1st, things were converged pretty well, and that May 1st forecast is actually one of our tightest groupings of forecasts that we had for this year. And this includes a lot of flight data assimilated into it. So that's good, but people may say, how good was it compared to everything else? How good was it compared to the model without ASO data? How good was it compared to the RFC forecast or the DWR forecast? So for each one of the major basins, we are summarizing those results in plots like these. I know DWR is doing their own analysis. So I think as the week goes on, we'll see more and more of this. We're also trying to compile this for Colorado and Utah. It is quite a bit of work to do this, but I think it's very useful. So I'm just going to show a couple examples of these. I'm not going to march through all of this for every basin that we forecasted in. This is the Feather River. And what you're looking at from left to right are different metrics. On the far left is the mean error. So taking all forecast pair matches, which is essentially these nominal first of the month forecasts, not like every RFC forecast, but the nominal matched pairs of all these. That's the mean error in the first grouping. The error variance, the standard deviation of the errors, that's good for looking at that uncertainty of how your forecasts are bouncing around from cycle to cycle. A maximum error column here, which is really useful to look at. What are the models that have the largest amount of error in it for that given year? And then going through on April 1st, May 1st, June 1st, and July 1st. So when you can absorb it all at once, you can kind of fly through these pretty quickly to get a pretty good perspective. But basically what this says for the Feather, when we look at the April through July mean errors, we did end up having a pretty small error from wharf hydro. Some of those are offsetting in the positive and negative directions. The standard deviation of the errors were fairly similar. The orange bar is the open loop version of the model for folks who are interested. And generally speaking, it does tend to be a bit larger than most of the other forecasts. Why might that be, one would ask? Is it a bad model? Does it need more calibration? All of those are valid questions. I would say this. A, the ASO wharf hydro, assimilated wharf hydro, obviously is constrained by the assimilation of the snowpack. That's a huge pin down of the uncertainty that's going into the model versus a free-running model. The river forecast centers are doing something similar in a more sort of manual way as well as they're creating their forecast. That is not a completely automated forecast that goes into that. So there is manipulation that goes into that. The DWR forecast is a statistical forecast of sorts, which has a number of different machinations to it. I'll let Andy and his team explain that. But also, as I understand, this is a consensus forecast as well, which is the final product that comes out. So there's a bit of weighing off different kinds of forecasts before they put out the final number. So there's reasons for the different behaviors we're seeing here, and it's important to understand those, but it's also very important to track those and see where we're picking up skill in these forecasting processes. So let's look at a couple more. The Yuba River, which was brand new for us this year, so first season forecasting in the Yuba. You can see the mean errors over there on the left. Our March error here for the ASO Wharf Hydro is pretty big. It flipped positive and then it kind of tapered off. You could see a little similar uptick in the April one for the RFCs in blue here. The max error in the middle, you can see some of those. Again, that's April through July. I don't include the March for any of these in the max error. So you can see how those are going. Go down to the Tuolumne. All right, this is one where we had a fairly large March 1st error in ours, and then things got fairly small. The RFC popped up in April and then tapered off pretty well. B120 was looking pretty good at this site. You do the same thing for Merced. We had a fairly low mean error here, several offsetting ones. Our April 1st error was about 6% for the ASO Wharf Hydro, and then things got really small for the Merced, which was pretty good. The RFCs also did really well in that basin this year. B120 for this basin, maybe not quite as much. So, you know, there's trade-offs in all these. It's really hard to say, you know, this is best, and probably it's impossible to say that overall based on this kind of analysis. Other kinds of analysis can clearly be done, but this is the kind of thing that we want to be doing, tracking, reporting with stakeholders so that they know what's working, what's not, and how it relates to sources of error in the modeling systems going forward. Okay, going to jump ahead. Colorado, we also have been doing work there for a number of years. Here we've got some comparisons with some River Forecast Center. And again, there's going to be some areas here where this is the East River in the Upper Gunnison, where the ASO Assimilated Wharf Hydro did quite well this year. Again, this time compared to the RFCs, but you can go to a basin next door and we'll see something a little different. So the April 1st ASO Wharf Hydro forecast was 8% error. By June 1st, it went down about 0.5%. And the RFC forecast, there's not a lot of snowtails in this basin to really cue off of, which really is one of the things that does feed into some of these other forecasting systems. You can see in their plot, if folks are used to looking at that, they were low and they were trying to play catch up throughout the season, and not until very late in the season could you see them really, that blue line there, ramping up their forecast to converge. And so getting the flight data in, we had our first flight here on about April 4th, I believe, or April 7th, and then another flight in late May. Those really tended to lock the forecasts in. Go right over the divide to the Taylor Basin. On April 1, the RFC was low by 9. We were high by 5 validated, but by June, the RFC was at 1%, really closed the game out really well here for them, but we had popped up to 13%. So why is that? And I'll get into this. In Colorado, we did notice this year that the Wharf Hydro model had some overly fast, or what we'd call premature ablation in the model. So it was depleting its snow a little too fast. And what happens when we took the ASO scene, added that snow back in with direct insertion, we started adding some mass back into the model and sort of double counting. And there's some pretty clear signatures of this in different places, and I'll get to some of that in a bit. But when we see some of these errors pop up in mid to late season, when we're doing that assimilation, it's really due to something in the model or the assimilation process that's doing that. It's not saying the ASO data is wrong, it's how we're using it. And so we're using it to actually diagnose the behaviors in the model. Probably one of the strikingest examples I've seen of the impact of ASO data since the Feather 2021 example, which most of you Californian folks are all familiar with, happened in the Dolores this past year. So we'll take a second on this because it's just interesting. This is the snowtail grouping that's used for indexing of forecasts in Southwest Colorado, the Dolores River Basin. 2023 is the aggregate grouping. A lot of snow last year in this basin. 2024 is in blue, a lot less than what they had last year, but the dotted line here is the 91 to 20 median. So you might think, well, they're still going to get above median or near median runoff if that is actually accurate. That snowpack estimate is accurate. This is a spatial map that Jeff pulled together looking at the difference between the ASO flight on April 4th, 2024 and April 6th, 2023. Brown is 2024 is drier. All right. Go forward to the next one, and you would see here, well, this is interesting. You go from pretty much brown, dark brown everywhere to late May, or sorry, the April 30th, 24, May 25th. Are those the right dates? I don't think those are quite, are those the correct dates? They are. All right. So there's a bit of a date spread here. But the point being, there is quite a bit of snow up high in the basin in 2024. And so how did that impact the forecasts? So over there is the classic CBRFC plot. The forecast, you can see the median runoff there is the dotted green line. And that median runoff is 235,000 acre feet. The RFC was a bit lower than that. They came in at 160,000 acre feet for their operational forecast. When we put in our ASO Wharf Hydro forecast, we came in at 115,000 acre feet, and this caused a lot of discussion in the Dolores Basin because it's rare that you see a spread that big between a lot of these forecasts. And so, you know, we went back, we double checked what we were doing, and then the CBRFC ran their experimental forecast with the ASO data for that fourth date, and they dropped all the way down to 125. So the confidence really started coming in for Ken Curtis and the Dolores operators that the Dolores was not going to come in anywhere near median, even though according to the snowtail grouping, it had essentially a median snowpack. There was a lot going on above those snowtails that just wasn't being captured by that. And so that was really one of the most, again, striking examples that we had seen. Okay, so where are we going for improvement? That's just a sort of the quick survey of results. Impact of regulation continues to be a major source of forecast error. And the more we dig into a lot of the sites throughout the West, we find nuances of regulation in various ways. And there's a real stratification in terms of forecast performance in regulated versus unregulated systems, unless, like Lauren's group at DWR does, provides us the nice FNF natural flow series to correct for that. And a few other groups have started doing that as well, but it's really essential. We can point to what the state of California is doing to create those data sets so that it really helps us create forecasts at downstream locations. So that's one main thing. I mentioned snow ablation rates. So several of the Colorado and Utah sites in Wharf Hydro exhibited some excessively fast meltout, which complicated the direct insertion data assimilation. And so that is a clear issue we're working on. And it's great to have the ASO data for this because in the springtime, when we get a nice batch of clear weather, Mark's team does something similar very well. We're looking at how the model's evolving between the ASO scenes to really try and pin down the ablation rates, both as a basin aggregated and also spatially distributed. And then we're modifying the data assimilation cycling to also help address some of those issues. So these are some examples now just for the impact of regulation. This is in the Yampa Elk Basin in Northwest Colorado. These are simplified plots, but the idea is the same. The orange dots are the ASO Wharf Hydro forecast. The blue line is the accumulated actual flows. These are all unregulated sites. You can see the errors here are fairly small. In terms of the mean values, you might get a max error that's close to around 7, 8, 10%. But then things taper off and go into their converged value pretty early. And these range from fairly big basins, 400,000 acre feet. That's big for Colorado. Don't laugh, Californians. And then you've got smaller basins all the way down to just a few, like 2,000 or 3,000 acre feet. So this is pretty true across scale. A couple of other unregulated systems in the upper Yampa River, a little bit larger errors here. That big jump you see in May is the impact of the last ASO flight that got baked into the model. The earliest flight was way back in early April in the system, so it was kind of a long delay here between flights, but then we were able to bump up and lock in. And when we go to regulated systems, this is sort of the classic behavior that you see. So if you're looking at the ASO WRF hydro forecast and you're comparing it against a flow time series, which may be coming from a USGS gauge or something else, but you haven't taken into account regulation, a lot of times you see this. You see the overly flattened flow accumulation curve, and you see this pretty bad drift, almost always in a downward direction, which is all the abstractions being taken out of the river. And then each forecast has more observations baked into it, so it gets pulled down. But it's getting pulled down kind of for the wrong reason. And so, again, we just put this up there. There's a highlight that this is an area that continues to need work. And if folks see these kinds of behaviors and they have questions about forecast performance in their area, this is something that's a good thing to look at. Another source of data that we're looking at is, so we're trying to go in and use multiple sources of data to diagnose model behavior. And so this is a case where we're using in situ continuous snow depth data. These are a network of stations that we've installed in the Upper Taylor River Basin. That's one site, Tin Cup, up above Taylor Reservoir. And then that's a bunch of soil moisture measurements at another site in that basin. And collectively, these two plots tell us that story, which I was mentioning earlier. So over here on the snow depth data, ASO is in orange. The station observation is in blue, notwithstanding scale separation between the measurement and the model. It's clear that the model is melting out faster. And then it does tick back up, some with spring precip, some with the data assimilation, and then it melts off again. The soil moisture tells the same story, though. We're getting water pulses into the ground early before the meltouts being observed at the stations. So this tells us, okay, there's some more work to be done at this particular basin so that we can remove that source of early ablation error. And that goes into the data assimilation as well as the model improvement. Okay, so leading us to the conclusions here, work underway for 2025. I mentioned some of the snow and hydrologic data assimilation. We are going to be moving more towards a supervised data assimilation as opposed to just this direct insertion methodology to reduce some of the mass and energy closure errors that we've been getting between the flights. There is some additional calibration that's forthcoming in some of the basins, and we're using these analyses to prioritize which areas we want to do the calibration and which areas we don't want to do. We are going to be blending in medium range weather data. That was another source of potential improvement in skill that could be picked up. We've just been sampling historical weather for the past several years of doing our WRF hydro forecasting, and now we're going to start blending in short to medium range weather data to capture some of the skill there. Logan's busy doing a lot of work on improving computational scaling and performance, so we're hoping to pick up even more quick turnaround times. That may allow for more ensembles, that may allow for some other enhancements down the line, but anywhere we can pick up compute performance is a good thing. I mentioned this also at the top of the talk. So the visualization and dissemination is going to change next year. We are going to go to a more frequent forecast cadence, but the weekly forecasts are going to be served digitally online, either through the APIs, an S3 bucket, as well as potentially some dashboards that we're working on, so people can get a very quick view of what each week's updated forecasts are looking like. After each ASO survey, though, we're going to continue to do the reports because that's where the most interesting action is really happening in terms of snowpack correction. If anything, just the spatial distribution of the snowpack, but oftentimes a lot of the quantities in different areas and looking at the reasons for those changes. We have the potential to add some new forecast locations. We've already started doing that in a number of different places. So for those stakeholders who are saying, I'd really love to have some additional forecasts in the headwaters or at certain control points in the system, let us know as soon as possible. We are virtually unconstrained in the number of forecast locations that we can put in. Everything takes a little bit of time to extract and produce a product for, but because it's a spatially continuous model and we've calibrated across the system or calibrating across the system, we think there's value at looking at a lot of the internal locations as well, and the results tend to prove that out. And then I put it in bold because it'll be probably the ask from here until the end of time. Wherever we can get more information on managed flow impacts or groups working on natural flow estimates. I know reclamation produces some. The RFCs have their modifications that they put in, but I know many of the stakeholders also do as well. It would be great to just continue that accounting so that our forecasts are more and more reliability up and down the system. That is it for the operational predictions.
If you remember back to Erin's talk earlier, she mentioned SBG, which is Surface Biology and Geology Mission. That's yet to come, but it's a spaceborne imaging spectrometer. There is EMIT up right now. I'm a co-investigator on that, which is on the International Space Station. There's NMAP. There's PRISMA. These are all spaceborne imaging spectrometers. And then yet to come is SBG and CHIME, which is European Space Agency imaging spectrometer. Talking about the ablation rates, much of that goes to handling the snow albedos. And so that's why we're going to be pulling those in. And with the myriad spectrometers going up into space, we'll have a much better cadence on that than simply what we get from ASO with those acquisitions. And so that will help to stabilize those melt rates through those intermediate periods between LiDAR acquisitions. And there was one other thing. Dave, will you speak again to the engineering skill and just the engineering accuracy that you were mentioning at the very beginning, and then what you were finding with the results? Because that was
well,
and of course it takes time to get that.
I think I know what you're talking about. I'm not quite sure.
Okay.
Lead me if I don't. So it's been my experience, and I think this has been a challenge in hydrologic forecasting for a long time, that you can spend a lot of intensive time and labor crafting forecasts at a single location. Sometimes it just takes that much work in order to get what we'd call engineering precision and accuracy so that you can operate infrastructure. There are certainly a lot of entities that do that. I think the challenge is that process is not exceptionally scalable, meaning it's very expensive to do that. Or when you go to other areas, maybe ungauged basins or incomplete data sets and things like that. If you're trying to estimate precipitation from a series of gauges or things like that, it can get really hard to scale out. On the flip side, there's certainly a lot of folks in the hydro community, and the National Water Model, I'd say, is one of those. It's like you have a standing system that's running everywhere, but it doesn't have engineering accuracy, right? It doesn't have engineering level precision and accuracy. Why would that be? Is it because it's a bad model? It's a possibility. Or is it because it's not properly constrained with the right amount of data and the right amount of care that might go into more traditional single point forecasting? So the gap we're trying to shoot with this, again, is capitalizing on the value that's coming in through a lot of these novel data sets. ASO is clearly one of those data sets where you can pin down uncertainty in snowpack several times in a season and run things forward. They're through calibration, model diagnostics, through other sorts of data. Like I showed here, you can pin down other sources of model performance errors as well and continue to make progress on that and do it across scale and transfer that into predictions. There's other novel data sets, as Tom mentioned, from satellites too. And so improved physics, improved data sets, in our view, are really helping to provide the constraint that we think are starting to lead us to be able to provide engineering precise, accurate forecasts, but do it, not just at a small handful of locations, but really be able to scale it out to a much broader area, to be able to provide both downstream and upstream headwater forecasts, and potentially even be doing it in places that are that are engaged because we've got a lot of constraint built into the model through data and physics and things like that. So that's what we're shooting for. That's the ambition. That's the goal. And I think, you know, California, we're starting to really demonstrate some progress in that area in several of these basins in Colorado that we've been working at a long time. And when things go awry, it's pretty easy to put our finger on why it went awry, which I think is another novel aspect, like what in a forecast system went off, and make those corrections.
Perfect. Thanks, Dave. And Wes? So Wes Moynier back there was in one of the very early meetings before we had any ASO hardware at all at JPL. It was just a concept that Bruce McGurk, it was a little meeting we had at the Sacramento Convention Center with Wes, Andy McMillan from Edison, and Gary Freeman from PG&E. And Wes, at that time, you talked exactly about this. So this goes all the way back to what you wanted back in 2011.
Definitely not yet.
All right. Well, thank you, Dave. Another round of applause. So that concludes the first day of the workshop. So thank you again for coming out. We will resume tomorrow at 8:50 in the morning. If you're presenting tomorrow, I know some of you are. You're free to come by and practice starting at 8:30. There also will be breakfast and coffee. So please feel free to come early as well. And yeah, today we obviously heard from our team, but tomorrow we'll hear from a lot of you and our cooperators. So yeah, looking forward to that. Thanks again. Have a great night.